Hello everybody! Today we would like to show you a video dedicated to phase noise measurements of a 10 GHz signal source with an exceptional spectral purity. Such a source is a sapphire-loaded cavity oscillator with a carrier suppression interferometer. The source is built around a high-Q sapphire resonator. This high-Q resonator, together with other components such as circulator, phase shifter, double balanced mixer and optionally a low noise amplifier, form a detector of the excessive phase noise generated in the main oscillator loop by the positive feedback sustaining amplifier. The noise suppression mechanism can be described in the following way. The signal from the oscillation loop is coupled into the interferometer LO arm. This signal has the same level of noise as the signal in the main positive feedback loop. From the circulator, the signal comes to the RF arm of the interferometer. This is a signal with a highly suppressed carrier and greatly emphasized noise sidebands. In the double balanced mixer, these noise sidebands are transformed into a voltage, which is applied as an error signal to the main loop phase shifter. This error signal will be tracking the phase fluctuations of the main loop oscillator relative to the sapphire cavity and is used to cancel them, or in other words, to suppress the main oscillation loop phase noise. Now let us go to practical measurements and watch in action a couple of really low noise sources referring to the X-band. The measurement of a signal source with such a spectral purity presents a non-trivial challenge, since conventional spectrum analyzers and even dedicated phase noise measuring instruments do not have the required phase noise sensitivity. Hence, two test oscillators are required to translate the phase noise from X-band to a lower intermediate frequency through a mixer. In our example, two sapphire oscillators with output frequencies 10.145 GHz and 9.95 GHz are used respectively. The spectrum analyzer is used to verify the oscillator's actual output frequencies. The signal is fed to the analyzer through a directional coupler installed in the RF arm. At the spectrum analyzer display, we can see the RF signal and LO signal separated by the I frequency of 195 MHz, as well as the other unwanted mixing products. Tuning closer to the RF signal, we shall see that the phase noise of the test oscillator goes beyond the phase noise performance of the analyzer. That means that we must switch to the dedicated phase noise analyzer, in our case to Agilent E5052A. What we see here is that even this dedicated instrument does have some difficulties when displaying the phase noise of the two sapphire oscillators at 10 kHz offset at a relatively low IF of 195 MHz. Remember that the actual signals are in the X-band, that is around 10 GHz. That means roughly that the spectral purity of the sapphire oscillators exceeds the quality of the local oscillators in the E5052A by the same factor by which they differ in terms of frequency, that is at least by a factor of 50, or if we think logarithmically, by 34 dB. Therefore, to reveal the actual phase noise of test oscillators, we must use cross correlations. We know that each order of additional cross correlations will enhance the phase noise sensitivity by approximately 5 dB. Let us use 10 cross correlations in our example. With 10 cross correlations completed, we see a far better phase noise picture. Now we are able to see that the phase noise is almost minus 110 dB at 100 Hz offset, almost minus 137 dB at 1 kHz, and lower than minus 162 dB at a 10 kHz offset. Advanced users of E52A know that the discrete spurs in the 10 kHz offset region are the residual products of the imperfect cross-correlation technique. They are most probably not present on the actual signal, but they are a good indication that E5052A still has insufficient sensitivity. Let us use therefore 100 cross correlations. It will be too long to wait for 100 cross correlations to complete in the video, therefore we are showing the final result. As can be seen, the measured value at 10 kHz has dropped to -165 dB. Now recall that we have been measuring two test oscillators, that is, at the output of the mixer we have the sum of the two noise powers. That further means that the actual phase noise of each particular oscillator is lower than the measured result by a factor of 2 or by 3 dB. After subtracting this 3 dB quantity, we will get the true result. It is -115 dBc/Hz at 100 Hz offset, -143 dBc/Hz at 1 kHz offset, and close to -170 dBc/Hz at 10 kHz offset, or in other words, close enough to a benchmark KT